decibels, and digital audio. So we're going to just briefly introduce you to the topics of decibels and digital audio. Let's start with digital audio. Now, just to break this down as simply as possible, let's draw just a basic audio waveform here. Pretty rough, that's okay. And this is equivalent to an analog waveform, the electrical form of acoustics in the air. So I say something out loud, there's disturbances with the particles and the oxygen and all that, and those hit your ear and you understand them because your brain can translate them due to how your ear works. But what happens is if a microphone captures this, then those are changed into an electrical signal, and then to be used on your computer it must be converted to digital. And so for the most part we use a format called PCM, which is pulse code modulated audio, and then we encase those into audio file formats like AIF or WAV. So the basic parts of those are the same though, the PCM. And we have two types of data here. We have sample rate and we have bit depth. The bit depth talks about the information on the vertical scale. And being a bit, we're talking about how many steps we have here. And so if we go 16 bits, that's going to be 16 little placeholders, ones or zeros, and that's decent quality, that's CD quality. It's one of the standards, but a lot of the stuff nowadays uses 24 bits, and that's millions times better because we have more ones and zeros, and with every additional place that gives us a lot more possibilities for different amounts of volume here. So this is really breaking down how much resolution we get in terms of amplitude of the signal. And the sample rate talks about how many little readings are taken per second when this is converted to digital. So the CD quality again is 44,100, and that's times per second. That's how many times per second it's looked at. Now we have some other formats here. 48,000 is the standard for video work. So audio work, CDs, that's 44,100. Video work, it's 48,000. Then we have some multiples of those as well, 96,000, 192,000, etc. Although for the most part you can't really hear a difference when you're working with those other formats. There's kind of a diminishing point of returns with sample rate, but bit depth, the more resolution the better, and the louder you can get it as well. And so at each point along the sample rate we take a reading of amplitude and we give that a little number there, and then the data is stored, and when it's replayed, sent out to the speaker, you simply take each piece of data, and it actually does look more like a stair step when you get there, but when it's converted to electricity back out to your speaker, if it's high enough resolution, it'll be very hard to distinguish what came in and what went out in terms of that electrical signal. So that's one of the main things when you're thinking about digital audio is the bit depth and sample rate. Now you don't want to convert them between the two as much as possible, so if you're working with video, you're basically going to be stuck with 48 kilohertz sample rate, and the bit depth will end up being 16, which we can truncate. So, keep it as a high of bit depth as possible, but try to start and end in the same sample rate. Now, if you're downsampling it to MP3 or other compressed data, then it's kind of a moot point, and just work in as high quality as you can, and then you'll be fine because you'll downsample it and take away some bits possibly in the end anyway. Now, decibels, because we're talking about level here, decibels are a big mystery for a lot of people because it's a term that we throw around for a lot of different formats. We talk about dBm, dBu, dBv, dBFS, which is the primary one we use in Soundbooth. The FS stands for full scale, and it's referring to a digital type of reading. Now the decibel itself is really just a comparison. It's a ratio, and we take a known factor, a known quantity, and we use it to compare other things. So it's really a way to take large numbers and make them small. So if we're talking about differences in pressure in the air or differences in signal, the numbers we're going to come up with, if using the actual mathematical equivalents, are going to be very large and very small. And instead of working on a scale that's huge, we're going to take it, condense it down into a very workable set of numbers. So dBFS, the very top, would be 0. And basically, by the time we get down even to minus 100, because we're going to go down here, we're going to be out of the audible range. So we're taking numbers that could be much higher and much lower and working them into less than 100 different digits. Now 0, that represents the very top, and if you ever see a red meter where it peaks out, that just means that we've been at 0 for more than a certain amount of samples, usually 3, sometimes 2, sometimes 4, and literally it's not going above 0, it's just staying at 0 to the point where the computer thinks it would have gone above if it could have. So that's all those red little peaks mean. As you're using this, typically speaking, half of the original would be more of like a 6 dB change, and then a noticeable difference would be just 3 dBs down. Smaller changes than that, some people can hear, most people can't. But just realize that 0 is the top of the digital scale, and we go down from there. Okay, that's really just a basic overview. Just to get you up to speed, there's obviously more resources online, and as well as in some of the other VTC courses. So check those out if you need more information.